We are on day 3 of chapter 13, and we are doing arithmetic and geometric series this time. Series. Series is different from sequences. You're about to find out how. All right, so what is a series? A series is the sum of the terms of a sequence. So you'll have a sequence, and when you have plus signs in between each of the terms, that makes it a series. Sequence has commas, series has plus signs. So a series can be finite, meaning just a certain amount of terms, or it could be infinite. And we usually use sigma notation to denote a series. You saw that last chapter. This guy is the Greek letter sigma. It's capital sigma. And it stands for the sum. So here's an example of sigma notation. Notice you've got the Greek letter sigma. Down here you've got k equals 1. That's called the index. And if the index is starting at 1. And then up here is what we call the upper limit, is n. And a sub k is the rule for the sequence. Right? Yeah. All right, so here's what this tells you to do. It says start by plugging a 1 into k. Gives you that guy. Then put a plus sign. Then plug the next integer bigger. So then plug a 2 in, a sub 2. Put a plus sign. Then plug 3 in, a sub 3. Put a plus sign. And you keep on going. The next one would be a sub 4 because you're plugging in, starting with a 1 into the k, and then putting the sigma says put a plus sign in between each of the terms. Dot, 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 all the way until you reach your upper limit of plugging in whatever number is up here. That's what you plug into the last guy. So I have an in there, so I put a in. For example, here's a series. 3 minus 6 plus 9 minus 12 plus 15. This is a finite one. It's not going on forever and ever. And it says using sigma notation. All right, so start with the sigma. I'm going to start with k equals 1. How many terms are there? 1, 2, 3, 4, 5 terms, which means I put a 5 up top. Going from 1 to 5 means I have 5 terms. And then the alternating signs, we're starting with a positive and then a negative, and then a positive and then a negative, and then a positive. How you get alternating signs is you take powers on -1. So -1 to the power of k would be when you plug a 1 in, you'll get a -1. When you plug a 2 in, you'll get a +1. When you plug a 3 in, you'll get a -1. But here we're starting off with when you plug a 1 in, I need a +1. Right? So you just take care of that by doing k plus 1. So when you have alternating signs, you'll either do -1 to the kth power or -1 to the k plus 1 power. And that just depends on, are you starting off with a positive or a negative? That's all that matters. And because I wanted it to start with a positive, I needed this power to be an even power. So when you plug a 1 in, you'll get -1 squared, which will give you the positive one that you need. But when you plug a 2 in for the second term, you'll get a -1 to the third power, which is definitely negative. So that's how you take care of alternating signs. -1, always -1 to a power, and it's either k or k plus 1, depending on if you need the first one to be a positive or negative. All right, now let's ignore the signs and look at just the terms. 3, 6, 9, 12. Ooh. That looks like 3 times 1, and 3 times 2, and 3 times 3, and 3 times 4, and 3 times 5. So the pattern is 3 times k. That goes next. That sequence is in sigma notation. And this 3k will always be like the nth term formula for your sequence. Those will always match too. So if it ever ends up being like this one was a pretty easy one to see the pattern, if it's not, then you'll just use the nth term formula for the sequence. Let's work the other way. Instead of me giving you the sequence and us writing it in sigma notation, let's actually expand this sigma notation out and then add them up. Yeah. So notice I got a j there. Yeah, they can give you any index they want. This one's j. This one was k. Sometimes they use n. What else? P. There's all kinds of ones that we can use. So looks funky, but whatever. So all this means is start by plugging in a 1 into J, and you would get a 1/2. The sigma says now put a plus sign. Plug a 2 into J. 1/2 quantity squared is a 1/4, so plus 1/4. Plug a 3 into J. 1/2 to the power of 3 would be 1/8. Plug a 4 into J. 1/2 to the 4th power is 1/16. I stop. Stop. Because my upper limit is 4. You're done. Add these guys up. You'd want, what, 8/16 plus 4/16 plus 2/16 plus 1/16. We get 15/16. All right, how about this guy? Ooh, I used a t this time. All right, and notice this time the t isn't in the exponent up here like it was up here, right? It's the base there, t squared. This index starts with t equals 0. So you start by plugging a 0 into t. 0 squared is 0. Then you plug a 1 in. 1 squared is 1. Putting plus signs in between. Plus sign. 2 squared, 4. Plus sign. 3 squared, 9. Plus sign. 4 squared, plus 5 squared, plus 6 squared, plus 7 squared. And when you add all of those up, you should get 140. All right. There's 2 examples. We went both ways from the series to sigma notation and then also from sigma notation to the series. If all it says is expand, you would just write these guys and not add them all up, but it actually said find the sum, so we added them up. All right, remember I said a series can be finite or infinite. We know it's infinite by this little dude right there. You have sigma notation again, starting with k equals 1, and we got a sub k, and instead of it being a finite number like 5 or 7, there's the infinity symbol up there. And what that means is you handle this the same way. Start by plugging in a 1 into k, and then a plus sign, and then a 2 into k, and then a plus sign, and then a 3 into k, plus sign, and then how do you handle the infinity? It's a dot, dot, dot. That means that it's going on forever and ever and never ends. So an infinite series, we can, there are some infinite series that we can actually find the sum of. You'll find that out later. But if we can't find the sum of the whole infinite series because the terms just keep getting larger and larger, we can still find a partial sum is what it's called. If we don't add up the whole series, we don't add up the infinite amount of terms, but instead we just take the first n terms, we call that the nth partial sum, and you denote it, you write it as a capital S with a little subscript of n, and that n tells you how many terms they want you to add up. It's called the partial sum of the infinite series. So let's find the indicated partial sum. This big capital S with a little subscript of 10 says add up the first 10 terms of this series. Yeah. All right, so right now I've got 1, 2, 3, I've got 4 terms, so I need to find 6 more of them. So I'm going to keep going. Yeah. What's the pattern? -3, -3, -3. So the next one would be -15, and then -18, -21, -24, -27. How many we got? 4, 5, 6, 7, 8, 9. One more. -3 gives you a -30. Add all those guys up. You'll get -165. How about this is called the 6th partial sum. So add up the first 6 terms of the series generated by, I gave you sigma notation this time. Yep, we can do that instead. So you start expanding this, right, by plugging in a 1 in first. So 10 times 1 minus 6 will give you 4. Sigma says put a plus sign. Plug a 2 in. 20 minus 6 gives you 14. Put a plus sign. Plug in a 3. 30 minus 6 gives you 24. Put a plus sign. We want 6 terms. We only have 3 so far. Plug a 4 in. 40 minus 6 gives you 34. Plus sign. Plug in 50 minus 6. 4 plus 60 minus 6 gives you 54. We now have our 6 terms. That's where we're stopping since they only wanted the 6th partial sum. Technically, infinity, this guy would be like plus dot, 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 right? But they actually want us to add up the first 6 terms. And so when you add all of those, you get 174. So hopefully you notice this is a pain in the butt, right? Adding up 10 terms individually, oh my goodness. Pain, pain, pain. Can be quite cumbersome, especially what if I asked you to find the 34th partial sum? You got to add up 34 terms. Oh, yeah. So we do have formulas to help us when the series is a special type. So if the series, well, if the sequence, A1, A2, A3, if the sequence is arithmetic, meaning you added the same number to get to the next one, like this first guy was arithmetic. Ooh, so was the second guy, both of these. This was a -3, this was a +10, right? So both of these were arithmetic. So if it's arithmetic with a common difference D, remember that your nth term is equal to the first term plus n minus 1 times the common difference. That's how you get the sequence, the nth term of the sequence. That was yesterday's lesson. To find the partial sum, you take n over 2 times a1 plus an. First term plus the nth term times n divided by 2. If you had me last year, this is the story I told you about the genius Gauss, Gauss, Mr. Gauss. When I put you into groups, he's one of the mathematicians. Back when he was like in elementary school, the teacher asked them to add up the first 100 digits. The teacher was like so over the kids. He's like, I just need a break. He wanted a break. So he's like, okay, take and add all of, 1 plus 2 plus 3 plus 4 plus all of them through 97 and 98 and 99 and 100. And Gauss figured it out in minutes. Teacher thought he cheated, but no, he was just a flippin' genius, right? And here's what he figured out. That 1 plus 100 was 101, and so is 2 and 99, and 3 and 98, and 4 and 97. All of those add up to 101. And how many are there? 100 divided by 2. You grouped up 2 of them at a time, right? How did I get this 101? By 1 plus 100. That's where the first term plus the last term, the n is how many terms there are. That was the 100 divided by 2. So Gauss came up with that formula. Genius to do that when he was just in elementary school. All right, so memorize that formula. Now, this is for an arithmetic sequence. Now, there is another formula, and all it is doing is combining this guy and this guy. So notice this a sub n right here, and that's a sub n. So all this other formula does is replace the a sub n here with the right-hand side, which would give you a1 plus a1, that's 2a1, plus n minus 1 times the common difference. All right, so here it is. The nth term is, you still have the n, you still have the divided by 2. Remember, we had a1 here, and then plus this a1 gives me 2a1, and then plus n minus 1 differences. Yeah. Either one works. Definitely memorize this one. You don't have to memorize this one. I certainly don't, but I know that I can replace this an with the nth term formula, right? And just do it that way. Which one should you use? Well, when would this one be useful, right? When would you need, like, does that make sense? Like, this one is useful when you're missing something, when you don't know what a value is. And what did I replace? The nth term, right? So if they're wanting you to find the 6th partial sum, you plug a 6 into n and maybe they give you the first term, but if you don't know the sixth term, then that's when this is friendlier. You can just go straight up from, otherwise you got to go and find the sixth term first by doing this and then plug it in there. So it's just a combination of that guy. All right, so let's find the indicated partial sum of, this means the eighth partial sum for 15, 9, 3, negative 3. All right, what's happening? What's happening? Well, notice I don't have the eighth term. I know the first term. Yeah. I know the common difference is what? Minus 6, minus 6, minus 6. So I went ahead and I used that second one. Yeah. Eighth partial sum means I'm plugging an 8 into n. I've got 2 times the first term. So 2 times the first term was 15 plus n minus 1. Well, my n was 8 right here. So I plug in 8 into n minus 1. Common difference we had figured out was negative 6 and then all over 2. And then what would that be? I just go to it. All right, so make sure you do 30 plus, what would that be? 7 times negative 6, so a negative 42. 30 minus 42 is negative 12, and then times 8 divided by 2 would be 4, so you get the negative 48. All right, when they give it to you this way, they want you to find the 24th partial sum for this sigma notation. All right, well, when they give you the formula, you don't need to use this guy because you can just plug in 24 into t to find the 24th term, plug a 1 into t to find the first term. You just use the first formula. We're going to use the first guy. N is 24. First term would be plugging a 1 into t. Whoops. So 1 into t would be, what, 1.5 minus 6, so a negative 4.5. Plugging in a 24 into t ends up giving you a positive 30. So we've got that, and you end up with 306. The nth term was the 24th term. Plug in a 24 times 1.5, which is 36, and then minus 6. So that's where I got the 30. The negative 4.5 was from plugging a 1 into t. And 1 into t would be a 1.5, and then minus 6 gives you the negative 4.5. All right. There's also a formula for, so all of those were for arithmetic, meaning I'm adding the same number to get to the next term. We can use a formula for a geometric series also. If A1, A2, A3 is a geometric sequence, when you've got a common ratio R, this was from yesterday, the nth term is found from the first term times the common ratio raised to the power of n minus 1. To find the sum of the nth partial sum, take the first term times the quantity 1 minus your common ratio raised to the nth power, and then all over 1 minus your common ratio. R can't be 1 because otherwise you'd be going 0 divided by 0. So other than that, you can find it. All right, so memorize this guy also. You're going to find the 7th partial sum for this series. All right, so on this guy, you don't need to know the 7th term for geometric. All you got to know is the first term and the common ratio. You're golden. Your 7 is your n. First term is 1. Let's figure out what is common ratio. Well, it looks like a 1 times negative 0.8 would give me that guy. Let's double check it. Is negative 0.8 times negative 0.8 a positive 0.64? Well, it is, and if it's not obvious, you can divide consecutive terms. 0.64 divided by 0.8, negative 0.8, you get negative 0.8. All right, plugging it in. 1, so 7 partial sum. Your n is 7. First term was 1, so that's where that goes. 1 minus r to the n, so 1 minus, be very careful. It's r, put parentheses around it, to the nth power. If that r is negative, that power gets distributed to the negative also. It's r to the nth power. So notice I put parentheses there. Don't you dare just distribute this minus sign to this minus sign. Not until after you evaluate the exponent. Now, and then it's a 1 minus r, so 1 minus and then a negative 0.8. Now, back up to this guy. It is an odd power, and when you do an odd power on a negative, it will stay negative. And so you will end up being a 1 minus a negative. But if this had been a 6 to the power of 6, yeah, then that makes this guy a positive number, and you're doing 1 minus a positive value. So be careful. Order of operations, right? You end up, when you put that in your calculator, you should get a 0.672064. All right, let's do a word problem now. Mark's grandmother gives him $100 on his birthday every year, starting with his 3rd birthday, and it's deposited in an account that earns 7.5% interest compounded annually. So your first term is 100. She gave him $100 first on his 3rd birthday. Yeah. Your R, 1.075. What the heck? All right, so I get the whole 7.5, move the decimal place over 2 places to the left for your R. So I get the 0.075, right? We move the decimal place over. Why would my R be 1? Why the 1? Yeah. Well, you got to think about it this way. You start with $100, right? So if you do 100, and then the bank pays them interest of 7.5%. So if you do 0.075 times the 100, what is that? 2. So that's $7.50. But that's the amount of interest earned, but then that gets added, right? So this is the interest earned. The bank adds $7.50 to the $100 that you had. And then on the 2nd year, they took this amount and they multiplied times 0.075, right? And they get, oh my goodness, whatever that is. Sometimes when I go off the rail, I don't think forward of what is going to happen. Okay, so this is $8 and 0.0625. Well, obviously the bank's not going to give you that much, right? So then they added $8.06 to that guy, right? So plus 107.5, and now he's got in his bank 115.56, right? And then they would do, okay, so what is happening? First year was 100, 2nd year was 107.5, 3rd year was 115.56. When you do 107.5 and divide it by 100, 107.5 and divide it by 100, it's actually 1.075. And you do the same thing here. The reason why is because you keep adding, you're adding the 100 you're adding the term right before it, right? And so that's the reason where this 1 is coming from. Yeah. Hopefully that makes sense. All right, so they want to know, how much is the account worth the day after Mark's 10th birthday? All right, so what is N after his 10th birthday? Well, you saw this last chapter also, right? That you can't just go 10 minus 3. It started with his 3rd birthday and then went to his 10th. If you do 10 minus 3, you get 7 years. But in reality, 3rd birthday, 4th birthday, 5th birthday, 6th birthday, 7th birthday, 8th birthday, 9th birthday, 10th birthday. It's been 8 times. So your N is 8. So you're finding the 8th partial sum. So you're always doing 10 minus 3 and then plus 1. Oh, okay. And it's the first term, 100, times the quantity 1 minus your common ratio to the 8th power. Technically parentheses around this, but I didn't need it because it wasn't a negative value. It was a positive R value. And then 1 minus 1.075. If you put it in your calculator like this, it will work if you put parentheses around this denominator also. And you should get $1,044.64 is how much he's got in his account after his 10th birthday. Not too shabby. All right. Here's your homework. There's one in every class. We'll take a sequence and call it you. Me. They're right. There is someone like that in every class. I love it. All right. I hope you all are having a fantabulous day. And come see me in office hours if you have questions. Bye.